Hello, everyone. I'm glad to see young people, so uh, they can create some new dimensions just by thinking about it. You can see this topic is a little bit strange, but I will explain it why I think it's relevant. And so uh, let me start with the core idea of this concept. And I will try to use my pointer. Yeah, it looks like pointer is there. Um, so instead of assuming that time has only one dimension, I consider three orthogonal temporal axes, like on this image, analogous to the three spatial axes we already accept. There, each temporal direction corresponds to a different physical scale or dynamics. The first axis, which is labeled T1, is associated with the kind of very small quantum scale and is linked to mass generation and discrete particle properties. The second axis is kind of like a common, like an hour scale, or correspond to interaction or intermediate scale, where quantum corrections or coupling effects appear. And the third one is a cosmological scale, where gravitational waves and large-scale structure dominates. The important point is that these axes are orthogonal, they are independent, and direction is in a temporal topology. So when we observe the universe in the usual three space and one time direction, what we call time is effectively a projection of this higher dimensional temporal structure. And so this introduces the geometrical picture, three independent temporal directions, each naturally associated with different range of physical phenomena, from particle masses to cosmology. So first, why do I do it, or what motivated me to do this? In modern physics, time is treated differently in different theories. In relativity, time is a coordinate that mixes sometimes with space through the space-time interval, like when we go to high velocities. In quantum mechanics, however, time is not an operator. It is just an external parameter in the Schrödinger equation. So conceptually, time already has an inconsistent role between our two most successful theories. There are also asymmetries that seems critical. The arrow of time is irreversible. We know parity and chirality show like a handedness, and physical behavior changes dramatically across different scales, from quantum to cosmological. And so, despite all of this, time is almost always assumed to be a single scalar dimension, and it's rarely examined in more detail. So, for the purpose of this talk, um, I'm questioning this assumption. What if time, like a space, has internal dimensional structure that becomes visible when we look across different scales? So here I want to show how time enters our two main theoretical directions in a different mathematical way. In general relativity, time is embedded inside the space-time metric. It is geometric, it curves, stretches, and interacts with energy and momentum, therefore with space. Time is part of the space itself. In quantum mechanics, though, time does not behave the same way. Time in quantum mechanics is not unobservable. Instead, it appears as an external evolution parameter that drives change, but is not itself dynamical. So we have structural mismatch. In gravity, time is geometric and flexible, but in quantum theory, time is fixed and external. So the key point is not that the one physics view is wrong, but maybe this dual role suggests time might have a deeper internal structure. So if time has a multiple orthogonal components, it may accommodate both geometric curvature and parametric evolution, like in those two physical approaches. So if we go from the current assumption before proposing any extension, let's have it clear what is the current assumption. We work with 3 spatial dimensions and 1 temporal dimension. Time is represented as a single scalar coordinate, and this leads to a familiar Minkowski or Lorentzian matrix where one dimension has opposite sign compared to the 3 spatial axis. So from this structure, we assume a universal causal ordering. From this structure, there's a single direction of before and after shared by all observers locally. So this model has been successful, and my goal is to ask whether this one-dimensional treatment of time might be a projection of a richer temporal structure underneath. So what are the tensions with the current picture that appear when we look carefully how time behaves in physics? We observe fundamental handedness in nature. The weak interaction violates Pareto meaning, mirror symmetry is not preserved, and this tells me that orientation and chirality are built into the physical laws. Second, time behaves differently across different scales. And at the quantum level, time appears to be external evolution parameter, while at cosmological scales, it seems to be geometric and linked to expansion and a curvature. This scale dependence suggests that a single scalar time coordinate may be an oversimplification, and so thus we also have this, arrow of time, that our fundamental equations are mostly time symmetric, yet macroscopic processes are irreversible. So there is a mismatch between microscopic symmetry and macroscopic directionality. And so, and finally, when you have like acceleration in space, it introduces observer-dependent vacuum effects, meaning that one observer sees an empty space and another may perceive as particles that is stationary. So this shows that time and motion are intertwined. This effect also shows like Unruh radiation. So these tensions suggest that we may look into more detail if time may have like a more topology in it. So here is the core hypothesis that I'm proposing, that it is that time may have 3 orthogonal coordinates analogous to how space has 3 orthogonal directions. So it doesn't mean like a 3 clocks that will be like independently moving, but it is an internal geometric meaning or structure. So in this view, the spatial dimensions we observe could be understood as an effective projection of the higher dimensional temporal topology. This way, the familiar 3 space one-time description remains still valid as a projected view. Local causality is preserved, and events have consistent local ordering and standard relativistic behavior. And so this extensional is just structural. The interval equation shown here is a conceptual illustration that time could contribute through multiple orthogonal components while still reproducing the familiar space-time description under the projection. So the intuition now that the time has 3 components, then together they form a coordinate system, volume, rather than a single line. So instead of thinking of time as one-dimensional sequence, I think it is of three-dimensional topology. What I perceive as space is understood as a projection slice through this temporal volume. The familiar 3D spatial world is an effective image of motion within this higher dimensional temporal topology. So observers do not stand outside the structure. Observers follow trajectories within the structure. And this word line become passed through this temporal volume within this topology. So the purpose is to provide an intuition of how multiple temporal coordinates could still produce the ordinary experience through the projection. So here is a mechanism, right, that the projection from temporal coordinates into spatial coordinates. So on the left, you see conceptual temporal plane representing two of the temporal axes. Instead of thinking of time as a single line, we consider structural temporal topology with internal geometry. So there is some object in this geometry. So the idea is that we perceive a spatial projection can arise as a projection of motion or structure within this temporal manifold. Mathematically, you can see there are just equations, and this mapping that those functions provide are just function of these three temporal coordinates. The grid inside the temporal plane represents internal temporal structure, while the red points represent events or states. When we apply the projection, these states appear as position in an ordinary spatial plane. So the space is reinterpreted as the effective image of trajectories or topology object in this temporal plane. And so the conceptual consistency check, I mean, you can see again the matrix that instead of regular space-time, I consider one spatial coordinates and three temporal coordinates. And the purpose is to illustrate that invariant interval structure can still be written in a very similar way. The expression shown in here preserve this Lorentz-like signature, meaning that the distinction between spatial and temporal directions remain encoded in the matrix. So it's not abandoning any like a relativistic invariance. I'm just inverting this dimensional structure. So I mean, instead of a three-dimensional space and one dimension of time that kind of goes through it, now you have a three-dimension of time and one like one spatial dimension that goes through this topological structure and just being projected. So it is not like it's just an analogy or concept that I am presenting. It's not like a finalized metric, and how it could be mathematically coherent without breaking any known principles. And so here's like an example that what I want to have a feeling what I'm doing, that I'm not deriving electromagnetism or gravity from three-dimensional time. I'm doing it the other way. I'm using the known physics, known field equations as a measurement language to describe how multi-temporal structure would appear if such projection is taking place. So you can think of general relativity and Maxwell's equations as constraints that outline the possible shapes in this kind of multi-temporal geometry. So these shapes are not, well, the physics is not replaced. They are just filter or that is trying to help me to see how this temporal model could look like. The law of physics experimentally are valid, and they become like a test for evaluating this idea. So another idea is the scale dependence that I did not, well, I will mention it a little bit later, that the different temporal coordinates may become more structurally dominant or different at different physical scales. short duration or high frequency processes may primarily weigh one temporal directions, while intermediate interactions another, and cosmological evolution like the third dimension. So all coordinates coexist at the same time, but their influence simply varies with the scale. So guiding question is given known physics, what multitemporal geometries are allowed and what observables would their projection produce? And so one critical thing with many extension of time is whether it breaks Lorentz invariance. So the law stays the same even if observers move at constant velocity. The key point here is that standard Lorentz symmetry is effectively recovered at energies that are below Planck scale. In this framework, additional temporal coordinates introduce only very small coupling terms, and these corrections scale with energy and became negligible at ordinary laboratory or astrophysical energies. So familiar specific relativistic transformation law still remains for all currently accessible experiments. Deviation that would take place would only happen in like a high order corrections that would be proportional to the scale, to the square of the energy relative to the Planck scale. So this means that model is constructed to be experimentally consistent by treating it as a low energy effective behavior of a richer temporal structure. Here I show the main concern that one could have, which is causality. Because once I am playing with time, causal accessibility is not defined by a single light cone, but now a temporal coin in three coordinate space. And so events are allowed only if their combined temporal displacement remains positive, as you can see here. However, we still require a monotonic ordering function, effectively a global parameter that never decreases. So this plays the role of the familiar arrow of time and prevents any kind of paradoxical loops in time. The secondary temporal coordinates do not dominate everyday physics. They enter only as a small corrections. So at low energies, everything remains the same. And in here, I want to mention the scale dominance. So these three temporal coordinates coexist, but I'm designing them, they contribute equally at all physical regimes. They do not contribute equally at all physical regimes. And at quantum scale, the first temporal coordinate would dominate. But then when you go from quantum to classical, you would have the second temporal coordinate. And when you go to very large cosmological durations, the third take place. So what you perceive as the ordinary time is therefore an effective parameter, a weighted combination of these three different temporal dimensions. So the weights are not constants. They depend on physical scale and interaction context. This is how everyday physics appear one-dimensional in time, even if the underlying structure may be richer, as shown in here. So we do not experience three independent clocks. We experience a projection where one component is usually dominant. Now, when we go to plasma physics analogy, in plasma systems, different mathematical descriptions dominate at different scales. At very small scales, we often have individual particle gyro motion. At intermediate scale, we utilize like an approximation of the drift. And when we go to large collective scales, now we have this magnetohydrodynamics that becomes an effective theory for description of such a system. So all of these descriptions are valid and they are not contradictory. So they are projects. So in this way, the 3D time are projections of the same underlying system. So it's my proposal is similar, that multiple temporal components may coexist structurally even if one dominates our everyday observations. And now, what I found interesting is this particle generation and chirality. So chirality appear in three-dimensional time topology is very interesting. So in conventional space-time, we assume three spatial dimensions and one time dimension, and time is usually treated as symmetric or scalar. In the 3D time, we consider one effective spatial dimension and three temporal coordinates. And so these three temporal axes have a specific coordinate system, right? T1, T2, T3. So you can have right-handed or left-handed coordinate system. So any three-axis coordinate system has this interesting orientation. So either left-handed or right-handed. And this orientation is not something that I add later. It is built into this geometry itself. So the key idea is that this intrinsic chirality or orientation can manifest after projection into the ordinary spacetime as chirality. So this interpretation, in this way, parity violation is the weak interaction, is not arbitrary asymmetry, but it reflects this orientation choice of the underlying temporal topology. The observed left-handedness of neutrinos would therefore suggest a left-oriented temporal coordinate system. So we already see that handedness is a real physical property in nature, like magnetic fields, vortices, and plasma structure naturally develop helicity, showing that orientation has an observable consequence. So in the 3D time topology, the temporal eigenvalue structure yields three discrete modes, which can be associated with the three particle generations. So the same geometric structure leads also to left-handed neutrinos and the familiar kind of a vector anti-vector form of the weak interaction. And the acceleration in this concept is experimental when how would the acceleration feel in this concept? So in physics, observations are not only dependent on velocity, but also on acceleration and reference frame. An interesting example is Unruh effect. It's an accelerating observer can perceive what an inertial observer would call a vacuum as a thermofield. In other words, the same spacetime can correspond to different physical realities depending on the motion. So conventional model treats this using curved trajectory in spacetime. However, in this 3D time, acceleration can be viewed as changing how an observer samples the temporal topology, effectively altering the weighting or coupling between different temporal axes. This offers a geometric interpretation of this Unruh radiation and why there are observers-dependent vacuum states and field perceptions. So there are mathematical and physical challenges. The first is metric signature stability and energy conditions. With multiple time dimensions, one must ensure that the internal structure does not introduce negative energy instabilities. Second, causality preservation is that you need a well-defined ordering principle, so events do not form like a paradox loops. This is why temporal cones and monotonic ordering functions become important. Third, the avoidance of tachyonic and non-physical modes. Extratemporal degrees of freedom can mathematically allow superluminal and imaginary mass solutions unless constraints are imposed. Fourth, the coupling between temporal coordinates. The temporal axis cannot be independent. Small coupling terms are necessary to recover effective 1D time at low energy. And finally, experimental distinguishability. If this would be like the reality, the theory must make predictions that differ even slightly from standard spacetime. So this proposal is not complete. It's just a constraint extension must satisfy the same empirical standard in existing physics. So now where to physical consequences. And if this is real, even small corrections could produce subtle physical consequences. First, there is the scale-dependent inertial behavior. In extreme regimes, like near Planck energies or very strong curvatures, effective inertia might slightly deviate from the classic expectation. Second, the parity or chirality biases under strong fields. Since orientation plays a role in the temporal manifold, very intense magnetic or gravitational fields might slightly weigh one-handedness over another. The third, acceleration link asymmetries is that non-inertial frames already reveal vacuum effects such as Unruh radiation. A multitemporal structure could introduce tiny additional anisotropies at high accelerations. And fourth, large-scale cosmological anisotropies. Over enormous distances, small orientation biases might appear statistically in structure formations or polarization patterns. On the right are examples of observables that could in principle be sensitive, like Lorentz symmetry test, gravitational wave dispersion, dark energy evolution, neutrino oscillation parameters, and cosmic microwave background polarization. And so these would be small corrections that would appear as a high order deviation. So this slide represents like illustrative parameterization. The idea is that if multi-temporal structure introduces Lorentz invariance deviations, they would likely be suppressed by the Planck scale. The quadratic energy dependence is a common phenomenological assumption in quantum gravity-inspired models. At laboratory or collider energies, the effect is zero. Only in ultra-high energy, like a cosmic rays approaching 10 to 11 giga-electron volts, the corrections become marginally non-zero. So possible observable channels include like arrival time differences in gamma ray bursts, tiny shifts in the energy limits for cosmic ray protons, or directional anisotropies in cosmic ray distributions. These would not be expected to be large signals, so very small. And so now there are just few things that, the few instruments that may provide some light in a tunnel. Like if a multi-temporal structure introduces small deviations in photon propagation, we would not see them in laboratory physics. We would look at the highest energy photons traveling cosmological distances, like the Cherenkov telescope array is designed for this regime. It measures tera-electron volts gamma rays and timing differences that could reveal small dispersion or anisotropy effects. So this Cherenkov telescope array represents the experimental frontier where this deviation could be present. And there is this Pierre Auger observatory. In multi-temporal structure, if multi-temporal structure produces tiny deviations from standard space-time symmetry, the best place to look is at highest energies that nature can provide. And so this instrument, this Pierre Auger observatory, measures cosmic ray at energies beyond any laboratory accelerator. It maps their arrival directions and energy spectrum across the sky. And subtle anisotropies or parity-like biases could be present. In general relativity, gravitational waves propagate exactly at the speed of light. And you probably have seen this like this model that you have like a two like a black holes that are spinning around each other, and so they produce this kind of like a pulsing gravity field, which is spreading or which is sending into space, so the question, this is a very extreme case, and so this extreme case also shows that there are very large acceleration, and there are these like boundaries between this like a normal scale and cosmological scale. And so this may be another possible way that you could show some of these things about this gravitational wave dispersion in 3D time. Because in standard general relativity, gravitational waves propagate exactly at the speed of light. All frequency components of the gravitational wave field is the same, so signal shape is preserved during the propagation. However, in 3D time, the assumption of single temporal axis is relaxed a little bit, and this allows the possibility that very high frequency components experience small deviations or corrections. So mathematically, this appears as tiny modification of the dispersion relation and effectively a frequency-dependent propagation speed. So small correction that scales with the ratio of the wave number and the Planck scale. Physically, this would manifest as a slight phase shift between the low and high frequency components. In other words, a subtle arrival time difference in gravitational wave chirps. You probably heard, these sound modulation of this LIGO experiment where there was this whoop, kind of like a thing. You've probably seen it. So this is what it's considered here as a chirp, like whoop, that you go from low into high speed because you are collapsing those two black holes. And here is another. I'm moving from geometry to cosmology, and so in the standard cosmological dark matter model, dark energy is treated as constant. Usually it says -1. Everything else is positive, but dark energy is saying this is -1 period at all times. In a 3D time, the effective expansion history can acquire a small evolution, and so the projection is a few percent deviation that increases with redshift. Different temporal coordinates contribute differently at cosmological scales, producing therefore slight shift away from -1 towards 0. So it is testable, and current and upcoming survey measure galaxy clustering, weak lensing, baryon acoustic oscillations, and supernova distance with fairly high precision. So if observations continue to tighten these constraints around -1, the 3D time model is limited. However, if small redshift-dependent drift appears, this could become evidence for additional temporal structure. Euclid is a European Space Agency mission now operating at the Sun-Earth L2 point, about 1.5 million kilometers from the Earth. L2 point is like a stable region, which is basically there's the Earth, Moon, and L2 point. For example, James Webb Space Telescope is also in this L2 point. And the main thinking is that the Earth is like production of a lot of noise because of what's happening. So the Moon is effectively shielding all the like a noise level. And of course, there is still, because all this system is moving around, orbiting around the Earth, so there has to be also this shield that protects when it's sunlit. And so the purpose of this mission is exactly to measure how dark energy evolves with redshift using weak lensing and galaxy clustering. So if there is even small deviation from the standard cosmological dark model, on the order of few percent, Euclid would be the mission capable of detecting it. This is just showing what instruments are there. There's a visible camera, a near-infrared camera that allows to map millions of galaxies and begin to constrain cosmological history. But no definitive deviation from this -1 has been reported yet. However, the error bar still allows that it could be present. Another instrument that I'm thinking could be critical is this dark energy spectroscopic instrument called DESI, a ground-based experiment that measures the redshift of tens of millions of galaxies or quasars. It uses 5,000 robotic optical fibers simultaneously, so it can observe 5,000 objects at the same time. So the light is split into wavelengths, and from the spectral lines, you measure the redshift, and from the large statistical map of the universe, you can reconstruct how expansion rate changes with time. And this could test this 3D time model. Current measurements of cosmic microwave background are consistent with this -1, the cosmological constant within these uncertainties, but some combination of data sets show mild preference for time-varying equation of state, but still no definitive deviation has been established. Neutrino oscillations is normally extremely stable. In this model, the deviation of tiny accelerator energies is tiny at accelerator energies, but it grows with the energy. So when you increase the energy, like from gigaelectron volts to teraelectron volts, especially for astrophysical neutrinos, the effect becomes a percent level modulation that the next generation detector like IceCube or Gen 2 could test. This is the IceCube Neutrino Observatory, which is currently in a South Pole. It's the largest neutrino detector on Earth, and it is not on a surface. All the detector is buried. You can see the scale about 2.5 kilometer below the ice. There are a string of light sensors frozen into the cubic kilometer volume of clear, sometimes they call it blue ice, Antarctic blue ice. And when the high energy neutrino interact with this ice, it creates a particle that emits a faint chunk of light, has a bluish color. By measuring the timing of that light across many sensors, scientists reconstruct the energy and directions of that specific neutrino. So for 3D time, this matters because neutrino oscillations at tera-electron volt energies could show tiny deviations. So this instrument could be also capable of testing that. Cosmic microwave background polarization is standard inflation predicts a smooth curve, and our model predicts a slightly different shape. That there are like a different bumps depending on this on this wavelength or L. It's not a wavelength because it's a kind of angular scale. It's a angular scale on the sky. So these are subtle but measurable with next generation missions that are targeted to measure cosmic microwave background. And on this image, there is called B mode, which is swirl-like anisotropies, as opposed to E mode, which is a radial pattern anisotropies of the microwave background radiation. So the experiment capable of testing it would be either CMB-S4 or Lightbird. And so the CMB-S4 was planned as an extremely sensitive polarization experiment. However, the timeline has faced funding challenges. So the scientific objective continues through other international projects. And so, for example, there is another one called Lightbird, which you may have heard about, and it's a Japanese mission. However, with I think it's in parallel with also NASA and ESA and others. Lightbird is a Japanese satellite mission specifically designed to measure this polarization, particularly the very faint B mode, swirl mode, associated with primordial gravitational waves. So it focuses on large angular scale and uses a spinning and precessing scan strategy to reduce systematic errors. This makes it an ideal instrument to test small deviation and polarization pattern predicted by alternative space-time model. It uses bolometers, and I don't know, I work with at Goddard Space Flight Center with bolometers with the detector laboratory, and so we were testing like the way how it works, that you have superconductor metals, and you keep them at the superconducting temperature, which is commonly on the order of like less than 1 Kelvin, and you just keep them just before the superconducting phenomenon is disappearing. So while you keep it at that specific level, that's when you have this very high sensitivity capability, which this instrument is taking advantage of. So one thing which is critical, that in order for this to work, you have to keep this like a supercode, because it works with this superconductor edges. So I also want to make sure that this idea is not replacement for relativity or quantum mechanics. So it does not allow like faster than light signals. It doesn't require like a many world generations, as you could see in some science fiction movies. It does not claim, but it also doesn't show data that would confirm that this is the case. So it's just an idea. It's just a geometric extension right now, I mean, capable of absorbing all the physics that we know of. So I want to mention relation to existing approaches. So 3D time relative to other existing theoretical ideas is that, for example, in string theory and higher dimensional gravity, the usual approach is to extend space with additional spatial dimensions. In this proposal, instead of keep space, this proposal is trying to keep the space minimal and extend the time structure instead. So we are actually reducing the spatial dimensions and by just modifying the time dimension. The many world interpretation introduces branching histories, like a multiple parallel universes or timelines. But in this 3D time model, it keeps a single continuous geometry, no branching or duplication. There's also this block universe model that treats time as a static scalar, and all events exist simultaneously. Here, the time is like a more dynamic. It has a structure and it has a direction. And there are some cosmologies that propose periodic or looping time. And so this is not the case in this framework. It's not cyclic. It just introduces orthogonal time axis. So it's just extensional of the time as we know it. And so why do we bother, or why do I think we should take a look at it? Why it's useful. Like I remember I was giving some lecture, I think during my defense, like a long time ago in Minnesota, and like there was a professor who asked me, like, why people in Africa who have would be would feel that this is important, right? They completely like threw me out, right? To think of why it would be important for some. But anyway, in general, we are interested in this question: why it is important? Why should we bother? So I would say it offers this theoretical economy. Instead of adding many new particles or forces, it reduces assumptions. In this picture, properties like charge or particle generations are tied to topology rather than being inserted by hand. The guiding idea is a single geometric topology. It remains compatible with existing experimental data. The predicted deviations are small and scale dependent, meaning they do not contradict precision measurements of everyday physics. It produces concrete predictions and possible Lorentz invariant scaling at very high energies and tiny frequency dependent dispersions of gravitational waves or subtle trends of dark energy evolutions. You can think like if you think of space-time, right? You have this one time dimension and three space, but you only see effect when you have really high accelerations or high energies, high momentum, that you see that suddenly this one time dimension seems to be interfering with the space, right, in theory of relativity. But right, so in here, I am proposing that there are these three, like a scaled time axis. And so on those transition between like those three different scales, there is an interfering of this projection mechanism. And that's where I think there may be a chance of seeing some deviation. So the open questions, right, or future thinking. This topology is incomplete right now, right? It's just an idea, and the central question involve, the metric stability, how it looks like. What are the coupling constraints? I'm just saying, oh, it changes from the from micro, like from the quantum level to the regular level, but where and how, right? Or the other way, when it changes from the like a kind of regular time into cosmology time, right? Those are the boundaries that needs to be like a look in more detail. So there are areas where mathematical physics, maybe plasma physics, and cosmology could intersect with each other. So in summary, the idea I am presenting is that time may have additional degrees of freedom, and that the space we measure could be an effective projection of this temporal structure. The goal is not to replace, what we know, but they investigate whether extending this time geometry can offer useful structural language for certain asymmetries, including like a symmetry and chirality. The emphasis remains on causality, mathematical constraints, and empirical testability. So thank you. Here are some papers I recently published that you may look into more details of specifics of what I was talking about.
Okay, questions? Any online questions? Questions of people?
How on earth did you get into this based on from your background?
Well, it's when I was 15, no, 13. I was kind of a bad student in school. And but I was interested in science fiction. And so just for fun of it, right, I was thinking about this dimensionality, right? And I was trying to, there's this three-dimensional cube. How would I make four-dimensional cube out of it, right? And so then I found out it's just it's just a projection. So with the little sticks, I was making this model of four-dimensional projection into a three-dimensional space. I was really excited about it. And so I was like in a summer camp, and there was this beautiful girl, which she didn't know anything, but I liked her a lot. And so I told her, hey, see this table? You can see this table as a boundary, between like a three-dimensional world, and we actually exist in a four-dimensional world. And then I was telling her how to construct this like a four-dimensional cube out of sticks, right? And she kind of looked at me and, oh, you are so smart. But that was first time that someone appreciated me, because before, oh, he's just a stupid boy, he should not really do anything. I kind of felt very kind of down. I had the depression, and this kind of discussion with this girl kind of opened my my world. And oh, okay, I'm going to continue to go to high school and do some. And then I went to School of Math and Physics, where we were exploring this, but it was so difficult. I don't know if when I was studying, analysis one, analysis two, there are these books that I remember was studying 2 months. I was preparing for, exam and it was so difficult. And so I passed, and but then I was started to be interested in magnetism and a magnetic reversals and what generates, how the dynamo look like, and how the currents are spiraling, and what's the handedness there, and how a different handedness in the northern hemisphere, different in the southern hemisphere. And this kind of inspired me to think about then this chirality problem. Because I also, my problem is I'm doing too many things at once. So I saw that there are these, the chirality molecules, right? That when you study uh, the amino acids, they are all left-handed in the biology world. But when you did this famous Steiner-Miller experiment, when you just put some urea into a flask and put electric discharges through it, you suddenly got also the amino acids, but they are both right-handed and left-handed, right? So suddenly there was this handedness that was kind of inspiring me, that it kind of, that's interesting. And then you read about this chirality problem, right? That there are only left-handed weak interactions. And so I did a lot of study in Siberia on Tunguska meteorite. And so, it was in 1908, there was this explosion in southern Siberia, and people didn't know what's going on. And so until today, people still don't know what it was, because there was just collapsed trees over the 50 kilometers in diameter. There's no meteorite sample, no any kind of something like a present that would say, oh, it came from elsewhere, right? And so there was this Robert Foote from Australia that actually came out with mirror matter. Mirror matter is the consequence of the chirality problem. That because the chirality problem is that the weak interactions are only in left-handed, right? It doesn't really make sense why there would not be right-handed weak interactions. So this Roger Foote came, I think it wasn't him, but someone prior him came with the idea that there has to be mirror world in another 3 dimensions where the left-handed interaction would be replaced by right-handed interactions. And so suddenly there was this expansion of the dimensionality, right? That instead of just our regular world, you have this mirror universe where there's this right-handed chirality thing. And then so I was developing an idea, how could I use this concept to explain the Tunguska explosion, right? Because is it possible that you could have like this mirror matter body, right? You can think about maybe as like a dark matter or something like that, right? Existing in different dimension, it will be now. We know that there is this dark matter everywhere, right? There's more than 95%. But what if it would be going into our solar system, would be going through some body? Would that be possible to get like an interaction that would look like this, like a Tunguska explosion? So it was kind of weird, idea, but people sometimes like weird ideas. So I was looking into it, and then. Because currently I've been in Siberia and took a lot of samples, lake sediments, and trying to figure out what's going on. So I was thinking back in like 2010 when I was pushing this idea about this mirror matter. And then I was again thinking about this chirality problem. And then I was listening to this three-body problem. It's a novel by some Chinese person who wrote like a trilogy of three, maybe some of you read it, right? And so there's a trilogy, and then there's also a fourth book. There's actually four, but that fourth book was not written by the same author. But anyway, in that trilogy, there are kind of like thinking about how the universe would develop and what would happen with our solar system and other civilizations. And then it says a story that someone gave someone a 3-dimensional fragment of time somewhere in that story. And that was probably the trigger. Then I was just thinking, what is it? I mean,
Okay, so again, that's just good. I mean, when I think of the work you do, it's geophysics, meteorites, that sort of stuff.
yeah.
Any more questions from people online or otherwise? I have a question that what is the difference or similarity or difference with the superstring high dimension? So superstring, you have like 11 dimension, the 4 conventional plus all these 7 other dimensions. What is the difference and similarity to your extra time dimension?
So the question is, what's the difference between the string theory and this theory? As you know, the string theory is very interesting because it doesn't say there is 11 dimensions, but it says there is more than 3 spatial dimensions, but there are multiple others that are kind of projected on each other, but they become important at some specific state. I think I see the main difference is that the string theory is just trying to explore like a much larger, more complex system. Because if you just go one dimension above a 3-dimensional wall, like a 4-dimension, 5-dimension, it becomes extremely complex. Like, again, there is this association because when I was doing my PhD, it was petrology. And in petrology, you work with the phases and components. And I thought it would be kind of interesting to see like the phase and component system to express into like a multiple dimensionality. When you have 3 components, you have 3 dimensions. When you have 4 components, you have 4 dimensions. You have 5 components, you have 5 dimensions, right? But now you use that kind of matrix calculus in order to, solve some of the petrological equations or the state equations. And so I know that when you use 6 or 7 like dimensions, it's so extremely complex, to see how everything goes together. So I think this other approach, kind of inverting, what I'm doing is basically inversion, right? We think there's a 3-dimension and time kind of goes through everything. Now I just completely make it inverse, right? That you have 3 time dimensions and time goes through these time dimensions. So it's kind of, to me, it looks like it looks simple. It doesn't require too difficult mathematics to do it like when you do with the string theory.
Yep. Okay, any more questions? I see no question online, so let's thank the speaker again. Thank you.
Thank you.